Hello, this is Tommy. Welcome back to Genomics. So today I'm going to talk about vectorization in R. So vectorization is a very nice feature in R, so it can make your calculation very efficient. So to understand that, let's start with this simple example. And in the end, I will give you an example using the GenomicsRanges R package to let's deal with some of the gene length problem or exon length problem. Okay, first you create this vector A. So A is a vector of 5 elements, 1, 2, 3, 4, 5. So if you do A plus 1, it is 2, 3, 4, 5, 6. So every element of A plus 1. So this is the feature of vectorization, because every element is added by 1. You can also do a multiplication, so A times 2. So every element of A times 2 here, so it becomes 2, 4, 6, 8, and 10. Same thing for A squared. Okay. So if you do this in Python, how do you do this? So in Python, okay, you can define this list A equals 1, 2, 3, 4, 5, right? And if you look A again, so it's a list of 5 elements, 1, 2, 3, 4, 5. So if you do A plus 1, it gives you an error because this is a list and you can't actually concatenate those two together. So to do the same thing in Python, you need to use this thing called list comprehension. So you do x plus 1 for x in A. So you kind of iterate x in A, and then each time you plus 1 here. You see, so you get the same thing, 2, 3, 4, 5, 6. So every element plus 1. So you can do the same thing for x squared for x in A, or x times 2 for x in A. Okay. Okay, that's how you do the same thing in Python. Let's go back to R again, and let's create the matrix. So matrix. So 2 rows and 3 columns, 1, 2, 3, 4, 5, 6. So to see here, the in R, it actually fill in the those numbers by column. So 1, 2, 3, 4, 5, 6. Okay, make sure. Sometimes for matrix manipulations, some functions they do column wise, sometimes they do row wise. You have to be really careful about that. Okay, so if we just divide this matrix by a single number by 2, if we do this, and actually every single element in this matrix is divided by 2. So that's also part of the vectorization. You can do mat plus 1, so every element of this matrix, original matrix, added 1. Okay. But if you want to divide, for example, a vector, that's a little bit tricky. Let's see how it works. So you define another vector B, 1 and 2. Okay, and you divide this matrix by B, by this vector. Okay, so matrix, just to remind you, is this. So if you divide by this vector 1 and 2, what it would gonna like? What does it look like? So you see here, actually the division of this vector is by row. So which means this row is divided by the first element of B1. So it's the same thing, 1, 3, 5 divided by 1, 1, 3, 5. And then the second row is divided by this number, and it becomes 1, 2, 3. Okay. But if you want to actually divide by so each column by a for example column sum, for example this column divided by the sum of this column, and this column divided by the sum of this column, this is a very common calculation in, for example, in RNA sequencing. You want to normalize each row is one gene, each column could be one sample, and you want to normalize each gene by the total number of counts for that sample, right? So you want to calculate the column sum. For example, you can do the column sum here, and this is if you look at the original matrix, 1, 2, 3, 4, 5, 6, and the column sum will be 3, 7, and 11, right? And you want to you want to divide this column by 3, this column by 7, and this column by 11. So to do this, because the division is by row, so you want to actually first transpose the matrix divided by the column sum, we just calculated, and then transpose it back. So then you get this. Okay, this column divided by 3, so it's 0.33. 2 divided by 3 would be 0.66. Okay, so that's kind of a tricky part. So you want to make sure you understand, okay, when the operation is by row, when the operation is by column. Okay. Now let's give you an example of genomics ranges. So in this case, let's first load this library, that transcript database library. Okay, and it contains the HG19 gene known gene information from UCSC. Okay, so you just assign this one to a new name called TXDB. If you do TXDB, it's a transcript database object. So supporting packages, genomic features. So genome version is HG19. Okay. So with this object, what you can do, you can use functions such as genes TXDB to get all the gene information for HG19 version human reference genome. So it returns a GenomicsRanges object. So it tells you the chromosome name, the start of the this gene, the end of the gene, and this gene ID is the untrans ID. Okay. So what we can do, you can also get the exons for each gene rather than the whole genes here. So if you do this, exons by TXDB and by gene. If you look at this one, actually now it's a G-range list object. So, and each element of the list will be one gene. So this is for gene 1, like untrans ID, and it gives you 15 ranges. So those are the 15 exons for that gene. Okay. So for this demonstration purpose, let's get all the lengths of the sum of all the exons for each gene. So to do this, you can just use the width function, the HG19 exons. So remember, the HG19 exon is a G-range list. Okay, so if you use width function, it returns a list of integers. So this gene 1, this gene 10, and this is the length of each exon. Okay, and then to calculate the sum of the exons, the length, you can use two ways. For example, if you do not use the vectorization functions, you can do this sapply thing or lapply. So it will apply this function, the sum, for each element of the exon length. Okay, so it will loop over each element of this list and calculate the sum. Okay, and let's see how long it takes. 0.0066 seconds. Okay, and so as I told you, everything in R is vectorized, and there are many functions. They are actually built-in vectorization feature. So you can just directly, instead of using the sapply, you can just use the sum function, and give the exon length and see how long it takes. 0.026, so it's almost twice as faster as this as applied version. So that's it for today. I hope you understand the vectorization in R a little bit and to take advantage of the vectorization in R. It makes your calculation much faster, but also be careful when you want to make sure whether the operation on matrix is by row or by column. Okay, that's it for today. I hope you learned something, and happy learning. See you next time.